We've defined our new number, that being I or iota. So now we can use it to solve all sorts of equations that we couldn't solve before. Let's have a look at this one. X squared plus 3x plus 7. Doesn't factorise, so okay, we'll put it into the quadratic formula. Now, previously that would be a problem because we've got the square root of negative 19. But now we can simplify that surd because we know what the square root of negative 1 is. It's I. So let's simplify that surd, and we're saying it's the square root of 19i. Now, be careful with your square root sign. That doesn't go over the I. Some people like to put the I in front of it just to make sure it doesn't get confused with the square root of 19. Well, whether you split it up into the two answers or not, of course, is up to you. The other way we could now do it is completing the square. Because what it means is every quadratic equation now can be written as the difference of two squares. X squared plus 3x plus 7 equals 0. Well, if I complete the square, I get plus 19 on 4. Now that was a problem in the past because we didn't have a formula for the sum of two squares. But we can now rewrite 19 on 4 as minus 19 on 4i squared, because the I squared being negative 1. We get it as the difference of two squares, therefore it factorises to be x plus 3 on 2 plus the square root of 19 on 2i, x plus 3 on 2 minus the square root of 19 on 2i, and so we get the same two answers, obviously. So it gives us an alternative way, I guess, of solving quadratic equations. What about creating quadratics? Thing that becomes real important. All quadratics that have real coefficients. So if all the coefficients are real numbers, then the solutions will appear in conjugate pairs. Unless, of course, they're real numbers. So if we're talking about complex numbers or imaginary numbers, then we know they're going to be in conjugate pairs. So what that means is, if it does factorise down to be a complex number, so x minus z conjugate will be the factorisation. If I expand that out, we can see what happens. The middle term becomes minus z plus z conjugate. Well, if you add a number with its conjugate, the imaginary part's going to cancel out. You'll end up with a real number. And the constant at the end is z times z conjugate, and we saw that was equal to the real part squared plus the imaginary part squared. So we end up with real numbers. So if we have to find this particular equation, we know the solutions are 4 plus I and 4 minus I. Well, I can simply go, well, I know the sum of the roots. Now, whether you write this down or not, of course, is up to you. You might be doing this all in your head. I know the sum of the roots will be 8, because the i's will cancel when I add them up. A product of the roots would be 4 squared plus 1 squared, 17. Therefore, the quadratic must be x squared minus the sum of the roots, so minus 8x plus 17 equals 0. Finding square roots. So how do we find the square root of a complex number? Well, if I said to you, what's the square root of 16, you could give me the answer quite easily. We know it's 4. But how do we find the square root of a complex number? If I square both sides, it's going to make life a little bit easier. Then I'll expand the left-hand side out, and I can equate the real and the imaginary parts. So if the square root of x plus iy is a plus ib, we will always get that a squared minus b squared is the real part of what we're square rooting. And 2ab will be the imaginary part. That creates simultaneous equations and will allow us to find what we need. So if I had to find the square root of minus 12 plus 16i, well, the difference of two squares, so a squared minus b squared will be negative 12, the real part. 2ab will be the imaginary part, 16. So over there on the right-hand side, I'll make b equal to 8 on a, and I'll sub that into the left-hand side, and we can create, well, it'll be a quartic equation, but we can treat it like a quadratic. So we've got a to the power of 4 plus 12a squared minus 64. Factorising that, a squared minus 4, a squared plus 16. So we get some possibilities for a. Either a squared is equal to 4, or a squared is equal to negative 16. Well, a squared equals negative 16 I don't have to worry about. So remember, a and b are the real and imaginary parts, and they're defined to be real numbers. Now, there's no real number that when I square it will give negative 16, so I don't have to worry about that one. The other one will give me solutions of plus or minus 2. And if I sub that back into b, I'll get plus or minus 4. So therefore, the square root is plus or minus 2 plus 4i. Now here's the interesting thing. If I had said to you, find the square root of 16, you would have given me the answer 4, not plus or minus 4. Complex numbers you can't order. So therefore you give both plus or minus 2 plus 4i on the square root. Okay, so it's a little bit different. So plus or minus 2 plus 4i for that one. Here's another way of doing it, which I think is a little bit neater, to be honest. So same idea, a plus ib is the square root of x plus iy. We just found that out. A squared minus b squared is x, 2ab is y. But I'm going to play around with it a bit. X squared plus y squared would end up being a squared minus b squared squared plus 4a squared b squared. And when I play around with that, I end up with a perfect square there. So in fact what happens is a squared plus b squared is going to be the square root of x squared plus y squared. So that's how I can find it a lot quicker. A squared minus b squared is the real part, so x, that's still the same. But then a squared plus b squared is that square root of the imaginary part squared plus the real part squared. How do I know whether to make the imaginary part positive or negative? It all comes to do with what we're square rooting. So let's do our same example and show you what I mean. Square root of negative 12 plus 16i. So the difference of two squares will be negative 12. That hasn't changed. That's the real part. But the sum of the two squares will end up being the square root of the real part squared plus the imaginary part squared. Well, 12 squared, that's 144. 16 squared is 256. Add them together, we get 400. Square root of 400 is 20. So a squared plus b squared is 20. And those simultaneous equations, I think, are a lot easier to solve than the previous ones. So if I add them together, the b squareds cancel. I end up with 2a squared is 8. So once again, I get a equals 2. I'm not worrying about the plus or minus here. So a is equal to 2. Therefore, b is equal to 4. That's where this note comes into play. How do I know to make b equal to 4 or b equal to negative 4? I have a look at the imaginary part of what I'm finding the square root of. If it's positive, which it was in this case, then a and b have the same sign. So b will be 4. If it was negative, then I would have made b equal negative 4. So that's how you tell. So I always make a to be a positive number. And then if the imaginary part is positive, then b will be positive. If the imaginary part is negative, then b will be negative. I think that's a bit easier to remember. So I always make a positive for that reason. So therefore we get plus or minus 2 plus 4i, same as we got before. So a different way of finding it. As I say, I think it's a little bit easier myself. Of course, we now can do questions like this a lot quicker. So square root of 5 minus 4i. Difference of two squares is 5. Sum of two squares will be 5 squared is 25, 4 squared is 16. So add them, we get 41. So square root of 41. Well, I didn't say it always works out to be nice. A equals the half of the square root of 10 plus 2 root 41. But that is the answer. So sub back in to work out b squared, and we end up with b equals a half the square root of negative 10 plus 2 root 41. Ooh. So our final answer, the imaginary part of what we're finding the square root of is negative. So there we get minus I root negative 10 plus 2 root 41. What an answer. But I mean, it is an answer. It's an exact value. We could, I suppose, try and work out what the square root of 10 plus 2 root 41 simplifies down to be, but nah, let's not bother. We'll solve this quadratic equation. So the formula's still the same, we're just using complex numbers. So negative b plus or minus square root of b squared minus 4ac all over 2a. So we now need to work out the square root of minus 5 plus 12i. This one will work out nicely. By the way, how I know whether it'll work out nicely or not? 5 and 12. What can you tell me about 5 and 12 in a particular number pattern? Yeah, Pythagorean triad. So straight away, if you see two numbers that form a Pythagorean triad, then you know the number's going to work out nice. Square root of minus 5 plus 12i. So Difference of two squares will be -5. Sum of two squares will be 5 squared is 25, 12 squared is 144. Add them together, you get 169, 13. See, there's the Pythagorean triad. That's why it worked out nice, because I'm going square root of a squared plus b squared. So a ends up equaling 2. Now, in this case, the imaginary part is positive, so b will be positive. So I can sub back in over there now, plus or minus 2 plus 3i, and we get our answers of I, or minus 2i. Now, of course, if you were very perceptive, you could have got those answers straight away using an idea about quadratics, where you say, hey, what multiplies together to give 2 minus 2i, and what adds together to give 2 plus I? And that is I and 2 plus 2. Now, I'm not saying you would spot that, but if you did, that'd save you some time. Okay, that'll do us for today. So 1B, a handful of questions there.